you want this to be really small. Let's look at a next example. We often think of regression model as explaining the variability in an outcome variable. In regression, R squared represents the proportion of the variability in the outcome variable that is explained by the predictor variables. Right, remember that? Okay. And regression model with a good predictor will explain much of variability in the outcome variable. So if the R2 is really high, that means residual is going to be smaller, because this is going to be a really good predictor. Most of the dots, actual dots, most of these dots are going to be explained by this line. If that's the case, the residuals are going to be smaller. That's what it's saying. That's what this is saying. And so if the R2 is higher, then residuals are going to be small and a good predictor. In a regression analysis, the total variability in the outcome variable breaks down as follows. Total variability equals to explained variability plus unexplained variability. Well, the explained variability is that the variability in the outcome that is explained by our predictor variable, and unexplained variability is that the variability in outcome not explained by predictor variables. So in other words, okay, residuals, those are the portion that was not explained. For example, sum of square y is a total variability. Sum of square is the sum of all the variabilities. So that's the total variability. And the total variability is a combination of sum of square for residuals plus sum of square for explained variability, which is these lines. How much variability does exist in this on this line, and how much variability exists in here. Let's see an example to get a better understanding of this. Researcher hypothesized that the family income is a strong predictor of students' grades on tests. Specifically, he believes that much of the variability in students' grades can be explained by their family income. Okay, and the researcher wants to create a regression model that uses family income to predict grades. He takes a random sample of 14 students and records their family income and their grades on the test. And this is the data. Here are the data. And here's the scatter plot. And Pearson correlation was plus 0.65. And recall that the researcher believes that much of the variability in students' test grades can be explained by their family income. So how much variability is there in the students' test grades to begin with? We can use the total sum of squares for the outcome variables as an indicator of the total variability in test grades. And total variability in the outcome is this. So this much variability existed in the sample to begin with. the sum of squares for test grades represents the total variability in test grades. So the researcher wants to know how much of the total variability in test grades is explained by family income. The explained portion of the variability in the outcome is called sum of squares regression. And sum of square regression is calculated as R square is the percentage of all the variability that can be explained by this regression. You know, remember that correlation? So it's logical. So the portion that's explained by this the model is sum of square y times r square. Of course, that's what it's gonna be. That's the explained variability. In other words, sum of square regression. And if you do calculation, it's, you know, it was R2 is 0.42. R square is 0.42, and sum of square y was 653.43. So explainable sum of square, the explainable variability is 274.44. That's how much of the total, you know, that can be explained. So about the unexplained portion of the variability in the outcome. Okay. And then, okay, this is a percentage. It's a ratio. So the number itself is the value out of total 1. So if you do 1 minus r square, that means it gives you the rest of the percentage. This is the ratio portion. So, you know, just do this. 1 minus r square, you know, get the value and multiply that with by the SS sum of square y, total variability. Then you get the unexplained portion, which you are gonna call sum of square residual. So again, r square was 0.42, and so 1 minus 0.42, and you get this value, and multiply that and this total, and then you get 378.99. So that's the unexplained portion of all the variabilities. And okay, next time we're going to use sum of square residual to tell us the typical amount of error that we have in our predictions. And we're going to start hypothesis testing for regression models. The regression, and it's a model, you come up with the model, and is this model really, you know, reliable? And the typical amount of error that we have in our predictions, and is it this typical amount of error? And in this case, our prediction, you know, is it more than typical or less than typical? You know, this error, you know, the amount of error we get is more than typical or less than typical. That's what I'm interested in, you know, because residuals can be really big, you know, sometimes when the dots are widespread, you know, scattered around widely. So yeah, let's see what we're going to learn in the next class.